Welcome back. Today is September the 25th, and we're going to finish up the practice homework for chapter 5. And so here's where we stopped last time, and we'll have plenty of time to finish this and maybe get started on chapter 6. Okay? So I'm gonna flip here. All right, so last time when we met, we stopped right here on question 4, and we were looking at the part for E here. Does A or E form faster from C? So we learned that A forms faster from C, and the C is the reactant of the tallest peak for F. Okay. So we're gonna go ahead and answer the letter G. Is the first step of the reaction exergonic or endergonic? And feel free to participate as I go along here. So what is it going? Hello?
Oh, sorry. I said endergonic.
Yes, it's endergonic. The first step is endergonic, and that is because the products that form here are higher in energy than the reactants. So the delta G here will be plus. All right. So it's endergonic All right. Letter H. Is the overall reaction exergonic or endergonic? Who can answer that? So the overall reaction is from A to G. Yes, it's exergonic. Very good, because the products are much lower in energy than the reactants. So we're comparing this delta G here, and this will be negative, because G minus A will give you a negative number. All right, so this is exergonic. Very good. All right, which is the more stable intermediate? Let's see, between E or C, which one is the most stable intermediate? C, exactly right. C is the most stable intermediate because it is lower in energy than E. So C is better, it's more stable. So I'm going to put and say that C has the lowest free energy. Or delta G. All right. Letter J. Which step in the forward direction has the largest constant rate? So this is a hard question, and you have to go back to chapter 2. Remember that I'm going to write this down here. So let's say you have this graph where 0 is very, very slow or no reaction at all, and there's the number 1 here for K. Here's the rate constant, and let's say this number right here is 10,000. All right, it's not on scale, but just imagine this is on scale. So anything that is less than 1 is slow. Anything that is much larger than 1 is fast. So that's another way to think about the K, the rate constant now. All right. So we're looking in the forward direction. Which step here will be the fastest? We have 3 steps. 1 is the fastest and why? So let me erase all this. So we start fresh from this new question. Anybody knows this answer? Which is the fastest reaction step here? A to C, C to E, or E to G, and why? E to G, very good. Why is that? It's because the activation energy to go from E to G to attain F is shorter, is smaller, it's a smaller bump. That's exactly right. So the energy to go from here to here is much shorter than going from here to here or here to here. Now once this passes this point, it just goes down quickly. But this is pretty much, you're just overcoming this much in energy. All right? So the answer here is E to G has the smallest activation energy therefore the fastest rate. All right. Which step in the reverse direction has the smallest rate constant? Now we have to think backwards. So we're going from G to E. We're going to go from here to here, then E to C, and then C to A. Maybe we have a chat here. Someone is asking. Very good, Esther. Is that the answer for this question? All right. Who has the answer for K? Which step in the reverse direction has the smallest rate constant? G to E, very good, yes. Maddie, G to F, it's not a full step, it's a transition state. So G to E is the right answer. So that's what I was trying to say. All right, G to E, and I'm going to explain why. G to E in the reverse reaction has the largest activation energy therefore is the slowest rate. Okay, so if you look at this, it'll take a lot of energy to go from here to here. And so That will be the slowest jump. And then to make E. So that is the answer for that question. All right. Any questions so far? No. All right. So we'll continue. Number 5. Look at the following energy diagram for an enzyme catalyzed reaction. I'm going to ask you more than the questions here. Let's dissect this enzymatic reaction. So how many steps are involved? As you can count, how many steps you can count? Anybody? There are 4 steps involved in this reaction. There's 4 bonds. So how many intermediates do you read? So we have one product or products. How many intermediates do you read?
Three.
3, very good. There's 3 intermediates. All right. So that's 1, 2, 3 intermediates. So this will be intermediate 1, intermediate 2, intermediate 3, reagents, product or products, and then you have transition state 1, transition state 2, transition state 3, and transition state 4. All right. Which step is the most exergonic? Which step releases the most energy? Step 1, 2, 3, or 4? Step 1.
Step 1.
Yes, sir. And yes, ma'am. So the most exergonic is the one that releases the most energy. So that will be step 1, because the distance from here to here, this delta G0 is negative. All right. Notice that the next one, step 2, is also exergonic, and 3 is exergonic, and 4th is also exergonic, but by a tiny bit. So therefore, first step is the most exergonic. All right. Which step is the slowest? Which step is the slowest? Which has the highest activation energy?
The second step.
Second step, very good. The second step is the slowest since it has the highest energy energy transition state. All right, so this one goes from here to here, and so it's the highest. So this will be a delta G double dagger because we're dealing with a transition state, not a final step or a completed step. So this is just a transition state. So therefore, it's a delta G double dagger. All right, that's pretty good. We'll have just oh, we still have a lot. I thought that was the last page. All right. Look at the following energy diagram. Is the delta G 0 for the reaction positive or negative, and label it on the diagram. So notice that this delta G from here to here refers to the delta G double dagger of the previous transition state, but the overall, this is the delta G 0. Your delta G 0 will be positive or negative?
Positive.
Positive, very good. Thank you, Christian. So it's positive. So you have a transition state here, 1, transition state 2. Right here you have your intermediate 1, if you want to call it. And here is reactants, and here is products. All right. Let me write a few things here. The overall delta G0 for the reaction is positive, since the reaction is endergonic. The products are higher higher energy, than the reactants. And the reaction will not be, therefore, spontaneous. Let's explain that. So it won't be spontaneous. All right. Do you want me to explain why it's not spontaneous? I think I will. So let's see. Let me open another tab. Oh, I have that for the next. Yeah. Hold on. Let me add a page. All right, so let me explain you why this reaction is not spontaneous. So you have all endothermic reactions. They kind of look like this, right? Where your products are higher in energy than the reactants. So if you have, let's say you have a reaction flask and you're ready to stir it. So this reaction will not happen unless you feed it with heat. All right? This reaction needs heat because it needs to absorb heat from the system. All right? The reaction will not reach the products unless it absorbs heat. So because of that, the reaction is not spontaneous. Now think about this for a minute. The Earth overall is warm, right? If you, with the exceptions of the North and the South Pole, the Earth is very warm. And so the Earth is ruled by thermodynamics laws. For example, if you pull a bottled water that is cold from the refrigerator out and you put it on a table, after a couple hours that water will be warm, right? Because that is the law of thermodynamics. The heat will dissipate. In this case, heat will come into the bottle and will warm up the water. So most processes that happen on the Earth are driven by thermodynamics. And so here's the opposite. So this is an endergonic reaction. RxN means reaction. And an exergonic looks like this. So you have transition state and the products are lower in energy. So here are your reactants. Here are your products. I forgot to say this is your transition state. Notice now that here your delta G0 was plus. Here your delta G, because you're subtracting this from here, your delta G0 is negative. So say for example, so here you went ahead and turned on the heat. But say for example you have sodium hydroxide, and you know that sodium hydroxide gets warm when it hits water. So here's your sodium hydroxide, and you are going to carefully pour a little bit of water to it, or an acid, and then you're going to have an immediate reaction. This reaction will be exergonic because the sodium hydroxide, upon contact with the water, will create and will release its own heat. So by releasing its own heat, you don't need to warm the reaction up. It will produce its own heat, and so the reaction will become hot. And so this is an example of an exergonic and spontaneous reaction. All right, so that's the difference. That's what that problem was referring to. All right, let's go back. So the endergonic reactions are not spontaneous. They are actually controlled by the scientist. All right, you can control how much heat you want to add to the reaction, the time that it will take to get there. So those are variables that chemists control. All right, question B here, how many steps are involved in the reaction? Well, you count the number of bumps that you see there, and there are 2 bumps. So there are 2 transition states. Or bumps, therefore 2. There are 2 reactions. steps. How many transition states are there? Well, we also see that there are 2 transition states. And we label them. It says label them on the diagram, so I already labeled them. So they are 2 transition states. All right. Let's go to the next question. All right. This question summarizes the 4 types of reactions that you will ever see. If you notice, all these reactions that we dealt with here, especially this one here, it had all 4 cases. Let's see, 1, 2. This one had 3 cases, but you will see all 4 cases, and that's it. There's no more than those 4 cases. So a reaction could have nothing but 4 of these cases, which is a lot. All right, so we're going to answer these questions. Here's match the answer with the correct letter A through D in the blanks for the following reaction energy diagrams. First one, a fast endergonic reaction with a small delta G double dagger and a small positive delta G0. Is it A, B, C, or D?
C.
C, senor. So that will be C. And that's right. So here's your small delta G that is plus. And it's endergonic. The products are higher in energy than the reactants. And notice that the hump or the bump is very small, so it's fast, so it's easy to overcome that energy barrier called the activation energy from here to here. All right, that's good. A slow exergonic reaction, large delta G double dagger and a negative delta G0.
B.
B. So someone, so you guys are waking up now. Please, good, go ahead. Can someone, who was talking there? Maybe you was talking to your neighbor?
B.
B, okay. All right, B is the answer. Yes. So B, and we had the answer here too in the classroom. That was good. So it's slow. So it has a high activation energy or long activation energy. That makes it slow. And it has also a negative delta G. So this delta G0 is negative. This one was plus. The second one is negative. All right. The third one, a slow endergonic reaction. I'm sorry?
It's going to be D.
D. All right. I'm listening to some background noise here. Let me hold on here for a second, and I'm gonna have to mute all, but I will let yourself get unmuted if you don't mind, because I hear some background noise, and I'm gonna check the screen here. I'm gonna share it again. All right. The last one is by default, right? A will be a fast exergonic, has a delta G that is negative, is exergonic, and is fast because the activation energy here is small. On the previous one, on D, D also has a high activation energy. Because a large delta G double dagger makes it slow, but then this is positive. because the products are higher than the reactants. All right. So any questions up to this point? Any questions? You guys good, clear? All right. Before I move on to chapter 6, we will start it in a minute. I noticed that on the lab reports, you guys are not really getting the concept of R and S on the feature projections. So I decided to bring that out today. Not that, not there. There. So I'm gonna open a new one here. All right, so this is a feature projection of glyceraldehyde. Notice that anything in the horizon, any atoms in the horizons means they are up. So the atoms in the horizon are up. The atoms vertically are down. All right. So if you look at this, this is what your molecular model set will look like. Your H on the left and the OH on the right are both sticking towards you. This is a tetrahedral structure, and it looks towards you. They are looking towards you. So what is this group? CHO. It's a carbonyl with an H group. This is an aldehyde group. So if I'm going to assign the priorities here based on atomic number, I'm gonna work on this one now. So the oxygen is number 1, takes the number 1 spot. Between these two carbons, which one takes the second priority? CHO or CH3? The CHO, very good. The CHO, this carbon, has 2 oxygens and a hydrogen connection. You see that? The 2 oxygens here because of the double bond, and then the H. And well, this guy right here is a carbon with 3 hydrogen connections. So this is going to receive the number 3rd spot, and the 4th will be the hydrogen. So now, to me, this is looking like, so if I'm going 1, 2, and 3, like that. I'm going counterclockwise. It looks like an S, but it's not an S because this H is up. So therefore, I have instead an R group there. So this group is R. This carbon is R. All right. So yes. So I have a question here. If I flip the H and the OH, that would be the S enantiomer. So let's do it. Let's do it together. So I'm gonna do it right here on the right side. So you're saying that if we flip this to this, it will be the opposite. All right. So here you have 1, 2, and 3. So right now it's starting to look like R, but it's not because this H is up. Therefore, you have an S configuration. So it's the opposite. You see that? The only times you don't switch is like, say, for example, in some of these examples I saw, like the H was here. So you have like this H, C, H, O, OH, and CH3. If the H is in the vertical position, it'll stay back. So you have now priority 1, 2, and 3, and this is looking like an R group, and it stays R. So this will be equivalent to that one. Yes. So that would be an R group. All right. So let's go and visualize the Fisher. Emil Hermann Fisher won a Nobel Prize on this, and the reason why he won the Nobel Prize for this work is because he was able to get something that looks complex, something on 3D to 2D. Now, a lot of you wants to go into medical fields. And guess what? In the medical field, you have to get used to seeing things in 3D, in 3 dimensions. You will have CAT scans, X-rays. All these things that you will be seeing are on 3D. So organic chemistry thrives to teach you that and train you on that, especially when it comes to drugs and how they lock into the active sites of the enzymes and things like that. Where you're prescribing a drug for a patient, you need to think in your mind and know what are the binding sites of this drug. And all of that thing happens on 3D. So for someone like Fisher to come up with this work and simplify something that is on 3D to something a little more doable on 2D, it was great, because we still live, especially in the universities, we still are pretty much tied up to a 2D world. We have our computer screens are flat, the paper that we use is flat. So the more we get used to going from 3D to 2D or vice versa, it's going to come in handy in the future. All right. Let's do this problem. So notice that I have 1, 2, 3, 4 carbons on these backbones of carbons, and so I can start assigning priorities. What I'm going to do is I'm going to check this carbon here, followed by, so carbon 2 and carbon 3 are my 2 chiral carbons. So when I deal with the carbon 2, I'm looking at their 4 groups. Their 4 groups for carbon 2 are this, CH3, and H, and OH, and this whole thing is the other group that is attached to it. That's how you need to visualize this. All right? All right, so let's do that one. So on carbon 2, I will have priorities on, let's see, the OH will have the number 1 priority. Carbon 3 here will have the second one, because that carbon 3 has an OH. An OH group, and the methyl is 3, and the hydrogen is 4. So right now I'm looking at something that looks 1, 2, 3. It's counter. It looks like S, but it's not an S because this H is up. So if the H is up, therefore you're dealing with an R. So carbon 2 is 2R. All right, let's do carbon 3 now. Let's see what we have. So for carbon 3, I'm gonna delete these blocks in green. I'm gonna deal with them in sky blue. All right, so here I'm gonna delete these things too. All right, so here we have that so these are the groups that are attached. the H, the OH, the methyl group, and this whole thing is the other one for carbon 3. Let me delete that and draw it better. All right, so now you have to assign this priorities. The OH will take the number 1 spot. Carbon 2 has an OH attached, so this carbon beats carbon 4 because it has an OH, so that makes it carbon. That carbon is 2 in priority. The CH3 is 3rd, and the H is 4th. All right, so right now I'm looking at, let's see, 1, 2, 3. So it looks like 1, 2, 3. It looks counter, it looks S, but it's not an S because this H right here, H is up. So therefore, you have an R group there. So I want you to know this because this is going to be on the next milestone, which is in October. When is the next milestone? It's on Wednesday, October the 7th. So a week from next Wednesday will be our next milestone. So carbon 3 here will be at 3R. All right? All right, I'm going to stop there. Unless there's a question. Quick question. You good? All right. Let's go to the next section. All right. So today I'm going to begin practice homework 6 for chapter 6. And like I said, this is going to be a challenging chapter because now you're going to be dealing with reactions. All right.
Dr. Odin?
Yes.
I have a question. Are we going to be having a quiz sometime next week on chapter 5?
I'm not sure yet.
Okay.
Yeah. But what I'm planning to do, we're going to have to accumulate at least 5 quizzes. I want to accumulate at least 2 extra ones, so maybe you can cancel the lowest 2 or something like that, if we have time. At least want to cancel 1.
Okay.
At least I want to cancel 1. Yes. I didn't have that in the syllabus, but I'm thinking that really, really strongly in my heart. I want to give you a chance to drop at least 1 of them. 2 will be greater. I mean, that would be great if we have a chance, but there's not that much time from here to November the 20th. Honestly, we're really going fast. So this weekend, I'm going to set up the homework for chapter 6, but you will have plenty of time to do it. It's not going to be due next week, but just to let you know, it's a long chapter, so we're going to go slow on that. All right, so we're going to be dealing here with something called the Markovnikov rule. In years past, the first time I taught OCHEM, I remember that I always ask my students, does anybody knows the Markovnikov rule? Anybody here knows the Markovnikov? Or if you're watching there? Anybody? I'll give you 1 minute. Anybody knows it?
So basically, the rich get richer.
Who said that?
Aaron.
Aaron, next time I see you, I'll give you $1. Excellent. So that was my pun. So that's exactly right. So every time I will ask that, and then my students say, "Oh, the student that will say the rich gets richer," I'll give him, you just got richer, $1. All right. So yes, Aaron. Next, when do you come to class, Aaron? Hello.
Oh, hello.
Aaron, when do you come to class? Is it Monday or Wednesday?
Oh, I come Monday. I didn't know you were serious.
Yeah, I'm serious. I'll give you your $1 on Monday. So,
see you then.
sounds good. Eventually, I stopped doing it because all my snack money was going away by the Markovnikov. But I will give it to you, man. All right, so that's what it is. So notice that this carbon here has 2 H's. and this carbon here has one H. And according to Markovnikov, this H that is here will go to the carbon that has more H's. So think of H's as currency or dollars. So this carbon here is richer by $2 on the right side, and the one in the middle has only one hydrogen, so it's a little bit more poor in hydrogens or dollars. All right, so the double bond attacks the hydrogen, and the bonds that are the electrons here are held by this bond. They're going to be transferred to the bromine like that. Okay, so notice what's happening here. Now your carbons stay the same. So now let's say I paint this hydrogen in blue. So you will have one hydrogen in blue. That's the new blue in red. And this one in red here. And so what's going to happen to this carbon here? It's going to have a plus. It's going to be electron deficient, because now what we're dealing with here is also carbocation stability. So carbocation stability says that tertiary carbocations are more stable. So let's say you have this, are more stable than secondary. Let's say this one, and more stable than primary. All right. So, and now what happened now with the bromine? The bromine is, notice also the attack. My attack always comes from electron rich to electron poor. You have to get used to this concept. Here's my electron rich. My double bond is my electron rich. My hydrogen is my electron poor. It's going to be plus. So that's what's happening. Now your bromine that is hanging around in the solution goes and attack that carbon. And now you have 5 carbons. You have 3 hydrogens here, a bromine, and you have the hydrogen in the back still there, and you have 2 that are red and the one that was blue came from this one. So does the Markovnikov rule matters here? The answer is yes. It matters, because we have differentials in the amounts of hydrogens. How about the next example? Let's see if we can do 2 examples real quick. This is my situation here. The carbon on the left has 2 hydrogens, the carbon on the right has none. The double bond attacks the hydrogen, and the electrons are transferred to the chlorine. And now you have this. You have a new hydrogen. You have the 2 that were original there, and now your plus is here. So this is a tertiary carbocation. It's very stable, and it's stabilized because this group stabilize the charge. H1 wants to participate and donates electrons, and that's what increases stability. And then your chlorine now is floating around in the solution, and then it attacks, and you make this. Chlorine goes here, and then you have your 3 hydrogens there. So it's ruled by Markovnikov, yes. Just give me 1 more minute of your time so that I can tie you with the 8 o'clock class. HBr and a double bond that is on a cyclohexene. Notice that this molecule is symmetrical. Both of them has a hydrogen. So is it ruled by Markovnikov? Yes or no? It's going to be affected.
No.
No, very good. Because it doesn't matter. Both of them have the same amount of currency or hydrogens. Excellent, Paige. So what you end up is you having, let's say I chose this one. I put the H there, and then the plus is gonna go here. This is gonna be a secondary carbocation. This one was a secondary carbocation also. Secondary C plus means carbocation, and then your bromine that is in solution goes in attack. And notice that this attack also came from here to here. And now you have this. And that's all you need to do. You don't need to draw the hydrogens anymore. All right, that's it. Thank you guys. Let me stop the recording and I will answer any questions.